Thanks for the introduction. Like I said, my name is Karan Jaffer. I'm a developer at ThoughtWorks. That's the short version of the intro. Okay. Oops. Maybe I should turn it on first.
Okay.
Alternate entertainment. Hello? Is it? Okay. It's okay, I can start. Oh, I think we're back. Cool. So 3 years ago, we started working with this financial client who wanted to scale their business up. They had a fair share of their market with a couple of products that they launched a few years ago, and they wanted to essentially grow their market share. They wanted to significantly increase the number of customers they had, and they had projected growth targets that they wanted to meet in a couple of years. They went through sort of an evaluation. They realized that the space that they were in did not provide enough growth opportunities, so they decided to add new lines of product. Now, this is not something they'd done in a really, really long time. So what they ended up doing was they called an organization in to try to evaluate their business processes and their technology infrastructure. When they went through this activity, they realized that their business would scale fine. Like they had the ability to launch the new products and support it from a business aspect. However, their technology infrastructure, their hardware as well as their software, would not scale to take the new inflow of customers, and essentially their systems would start broken. As a result, they decided that they had to launch a new platform, one built on a more modern platform which allowed scalability, which over the next decade could help them launch all the products that they wanted to and achieve the growth target that they had set for themselves. Now, this kind of sounds like a lot of the projects that we might have worked on, right? Quick show of hands, how many of you have worked on projects where the key reason you were trying to do something was really because your software could not scale or had performance issues or was just like legacy code which took a while to refactor? Right? I mean, decent population here. And you guys share this experience as well. So it does not sound like a new experience. However, like the reason why this particular project really stood out in my mind for me was purely the number of integrations that we had to do. Right? The ecosystem that we had to work with, not just inside this financial institution, but the organizations we had to communicate with to make sure that the products went live. So to make sure the first product actually was released to market, we had to integrate with over 27 third-party systems. To bring on the existing products, we had the integrations would double. So you were really looking at over 75 integrations within the first 3 years of this new platform going live, which meant integration had to be planned to be at the heart of this development effort. Otherwise, this plan for building this new platform would not work. Now, this along with the 370 services in production meant that you were looking at a absolutely massive system in production. One which worked at scale, was available all the time, and took a lot of traffic. Now, the communication interfaces, when you were speaking to these over 75 third-party systems, included some standard interfaces like over HTTP, like REST and so. But it had JMS, it had file transfer, and even a few mainframes. Now, most of us don't deal with mainframes all the time. But the reason why, this is a financial system, so they have to continue to sort of integrate with these systems. During this experience of integrating with all these external systems, we realized that not all of these systems play nice with us. Right? They react in weird ways, and we have to protect ourselves to make sure that our service quality does not go down. Because that's the main reason why we are building this platform, and we can't have outages or downtime because a third-party system is not available. So here are some of the today we're going to be speaking about some of the challenges that our team saw and the way we actually tackled them to make sure that we could achieve the target that was set in front of us. Before we do that, what we're going to do is look at a high-level view of what their existing software kind of look like. We'll do this by taking a simplified example of their stack. So let's take an example of an order management service where you have a UI where you place an order. You'd have this UI speak to, say, an order service, which accepts the order and tries to confirm if inventory is actually available. So the order service goes to the inventory service to check for available inventory, which has to go to its database to make sure that the information is available. Let's say that the information, let's say you have enough items to fulfill this order. So the inventory service says, yeah, you can go ahead, everything looks great. The call comes back and the order service records the fact that there's an order, and then you return the call to the UI. Now, at some point, if you keep getting orders for the same thing again and again, your inventory will run low. So your inventory service probably has to speak to a vendor to make sure that you replenish your inventory, that you restock yourself, right? So far, this looks like a typical 3-tier stack. You have the database has the current state, and services communicate with different vendors. Now, if I were to draw a parallel and kind of use a metaphor for this system, you would have the inventory service could be represented by Spock, and Kirk can represent the order management service on the right. Now, if you do not know Star Trek, don't worry. This is not a Star Trek talk. As much as I'd like to do that, this isn't one of those. I'm just trying to draw a metaphor. The colors behind the services kind of give you an idea as to what it is. It's just friendly faces instead of going through just system names, right? So if we stick with this metaphor where these two characters are actually part of the Federation, the communication that you see between them, the line between them, can be actually represented by one of the Federation approved languages. Let's take Vulcan as the Federation approved language here. So the conversation between Kirk and Spock is now in Vulcan. If that's the case, when Spock has to speak to a third party, that conversation will be done in a different language, a slightly different dialect. If our vendor is actually Commander Kruge, who's a Klingon, then Spock is responsible to speak to this vendor in Klingon, right? Another language. If you're a pretty large organization, you'd probably have more than one vendor that you have to sort of replenish stock with. So let's make the problem worse. Let's have two vendors here. The other one is now Commander Tomalak, who is Romulan. Now, as you can see, Spock would have to know a third language, Romulan, to have this conversation. This is where we see our first challenge in the way we design our services, which is each of your services has to be multilingual. Now, if I were to map the services on the right-hand side with the languages that they need to speak, when Spock is speaking with Kirk, the language used is Vulcan. This language is sort of the languages that your services speak to each other in. It's the language that your business speaks to you in. It's the same kind of lingo that you use to actually represent your code. It's your domain language. Now, if Spock has to speak with these other third parties, those languages can be termed as being external languages. Each of these languages actually is represented in code, so it's not just one of the concepts that we're talking about. So we'll go into a few more details about this, but what you'll see soon is every time you talk about this language, it is essentially the protocol that you use to communicate with this third party. And right about now, you have one of the languages, which is the domain language, which if you look at Eric Evans's domain-driven design book, it's called the ubiquitous language. That's the language that you want to be writing your code in and that's the language you want to model your domains in. However, your system also has to learn these other languages because it has to interact with vendors or vendor systems. Right? It's almost as if you wish you had a universal translator from Star Trek, so that the conversation became easy. You could continue to speak in your approved you could continue to speak in Vulcan, and the machine would convert that into translate that into the vendor-specific language. Let's look at another challenge, which is related. Shared responsibility and common integration partners. So, when you set up communication between yourself and a vendor, one of the first things you do is that you have a contract set up, right? So you have that document essentially tells you what is the protocol for communication. In this case, let's take an example of an item ID which has to be passed whenever you send a request out from your system. So whenever Spock has to send any kind of message which has an item ID, let's say the rule states that the item ID, even though it's a number, has to be put in quotes. So the request would look like this. Now, whenever you get the response, let's assume the rule is that if the response has an item ID, the vendor will make sure it's always 5 digits in length and in quotes. So if the number 123 is since the number 123 is smaller in length than 5, you would append zeros to it, right? Now this doesn't look like a real problem, but it's kind of a nuisance because every time Spock has to speak with any other system in the federation, essentially, one of your services, it has to just remove the quotes and use just the number 123. Whenever it gets a response, it has to remember that the quotes have to be dropped and the padding zeros have to be dropped as well. It looks like an arbitrary example, but this is not far from many of the integrations that we have to do with, especially with legacy systems which are fixed in length, right? So to make matters worse, when you have to do the same thing from multiple services because one vendor kind of satisfies more than one business requirement, you're looking at the same logic now spreading to multiple systems, and the concept of converting this into your domain language now is spread into multiple domains. So, I mean, the thing that you would really wish you had was something to represent integration as a first-class domain. So why don't we have a system here which actually does that? So this is where we introduce the protagonist of today's show, Comms Officer Rahura. She is responsible for making sure that the translation between your domain language and your external languages actually happens successfully. So any language which is sort of, so if you draw a clear line in the sand, this is kind of like your network boundary. Anything above that is inside your company's network, and anything outside is, outside the company's network. So the languages which the way you design your code when you're speaking with systems inside your organization is based on the UL or the ubiquitous language, and anything which is outside, you can choose to implement a vendor-specific language to speak. So now that we've talked about some of the challenges that we faced, let's quickly go through a quick crash course of what the platform looked like, the platform that we set up. So let's look at what does a event-driven domain service kind of look like on the inside. So let's look at what event-driven systems actually work like. So if you have let's say three systems, you have Kirk and Spock, who you've already met. The new guy is Bones, I believe. Yep. He's the medical officer. So each of these represent a domain or a system in your, a piece of software in your system. Now, in a traditional SOA-based architecture, you would have them call each other for whenever they wanted to exchange information. But when you're doing, when you're building an event-driven system, this changes just a little bit. So each of them will announce an event when something happens. An event is it announces that something has happened in the past and is a matter of fact. For example, a customer's address changing is an event. So customer address change event is how we normally name it. And the reason this is important is that the domain who owns the customer entity announces the fact that this change has happened. And no one else really contests it. If you care about it, you will kind of listen to it. Now, what happens is that this event actually is announced in an event on the event bus. Now, event bus is kind of like a room, much like this one, where each of the systems announce what has just happened, and there are other systems who listen to it. Now, each of these systems. Now, let's actually go through an example of what this looks like. So, if your first system announced that an order was placed, this event is now spread over, sent to the other domains. Let's say it comes to Spock. Spock cares about an order being placed and therefore listens to that event. And when the same event goes to Kirk, Kirk does not care about orders, much like the character on the show. and therefore he actually ends up ignoring the event, right? So what you'll notice is that the event bus is a channel for announcing change. Each of the services will fire an event and forget about it. There is no coupling between the services themselves. None of the services know that someone else is going to react to a change. I have done my job by announcing the fact that something happened. If somebody reacts to it, that's fine, and if no one does, that's okay. You also only pick up events that you subscribe to. If you've not asked for an order placed event, you will not get it. Right? So you have to subscribe to the events that you really care about. The other concept that we want to concentrate on today is one of the styles of how we modeled our events. If you attended Martin Fowler's talk earlier, he talked about some styles in which we design our events. This is one of them: event carrying state transfer. What you do here is that the event name, the customer changing their address, kind of explains what happened. There's a customer ID to explain which customer actually changed their address. But if you notice in blue, there's a section which actually has the address, the new address of the customer. So what you've done is that this event completely explains what the change is and where the change was applied. The event is self-contained all in itself, and this style of event design is kind of important if you're doing event sourcing. This is in contrast with something like event notification, where you would announce the fact that an event has happened, but not really tell the user what the actual change is. You just provide a sort of link where an HTTP resource, for example, where the user can go and actually fetch the latest state of the object. There is no right or wrong design. The question is, what suits your system better. In our case, since we were building an event-sourced, event-driven system, the event carry state transfer model worked better for us. If you want more details about about this topic, you can read through Martin Fowler's blog post, "What is event design?" There's also, in the past 2 weeks, I think Martin's talk at GoTo Conference was put up on YouTube. It's a pretty good talk where he actually explains the entire thing as a 15-minute talk, much like he did here. So if you've not actually attended the talk on the series, you can go back to YouTube, look up that video. It's a good watch. Okay, coming back to our system design. So now that we know what event-driven systems look like, let's look at what our third-party communication stack looks like. So you have services on the top, which sort of announce changes as events on the event bus. You have vendors at the bottom, and what you have in between is the gateway, the service gateway, who listens to the events, figures out which ones actually need to be sent to a third party, do the appropriate translation, and then send it out to the third party, right? So if we go into sort of the details of how the service gateway looks on the inside, and we have the event bus on the left and the vendor on the right, the gateway will be in the middle. And the gateway has 3 major steps. It has a reader, it has a transformer, and it has a writer. These are the 3 basic steps of making sure the message can be correctly converted and sent over. This is sort of the model that we'll start off with, and over the next 10 or 15 minutes, we will evolve this model to add more details into it. But if you notice, a reader is pretty generic. The way you read messages off of a queue is pretty standard. The transformer keeps changing every single time because you have a different request, a different incoming event, and the outgoing message might be different. So the way you transform is really custom logic every single time. The writer really depends on how you're sending the message out. If you're sending the message over HTTP, there will be one writer. If you're sending it over JMS, there will be another one. Since we're doing over 75 integrations, we didn't want to keep writing this collection every single time. We want to give returns back to our entire development team and build a framework which accelerated the pace at which we could do integrations. So what we ended up doing was we built a set of standard readers and writers based on where you want to read the message from and where you want to write it. And for the transformer itself, we we added this layer on top called the adapter. Now the adapter contains two sets of configurations. One is the transformation rules. The transformation rules will tell you how to transform the message from, say, a customer address changed event to whatever it needs to be when we send that message out to a third party. The root logic actually explains where you read the message from and where it is supposed to go. So details about how that third party vendor actually accepts messages over JMS or HTTP, and a bunch of other configurations that you need to be able to correctly send that message out. The service gateway here, now instead of having business logic about how how to transform messages and actually translate and send the messages, is now more responsible to be a container. A container kind of like Tomcat, where you can put in different assets and it would just know what to do and actually how to translate messages and send them. So let's move on to the next challenge and see how this affects our system design. The next one is vendor abstraction, how we achieve vendor abstraction in our system. So what we're going to do is that this is the stack that we've been working with so far. And what if one of your services announces that the inventory is actually low? If it realizes that the gateway realizes that since the inventory is low, it has to do something because it has been told based on the configuration that we put in as an adapter, it knows that it has to act on this information. So the gateway decides to react. One of the things the gateway needs to know is what the message looks like. So let's take a sample event body where there's an event ID and there's a couple of other fields that we don't really need to focus on right now. Now, based on the configuration that we have inside the transformation rules, you could say that an item ID of 403 needs to go to this specific vendor. It's kind of like saying if I want cheesecakes, then I go to a bakery as opposed to and there's a preferred bakery which you can configure. But if you want, let's say, pizzas, you have a favorite pizza place that you go to make sure that your stocks are maintained. So this is kind of like that. You're saying that item ID 403 comes from this specific vendor. So you'll make sure that you transform that message and actually send it out to that vendor. Let's actually look at what this means in code. Like how would you configure your code to be able to do that? So at a high level, you have what we would do to make sure that since there are two vendors and we have to make a decision between who gets which message, we can have a service gateway where we put two different adapters. Now, on the first adapter, we configure the fact that anything which is an item ID between, say, 200 and 300 will be picked up by this, will go to vendor 1. So if adapter 1 picks up the message and actually transforms it, it has been configured to send the message to vendor 1. If the item ID is between 300 and 400, the system's been configured to have adapter 2 process the message, and as a result, the message will be sent to vendor 2. This allows you configurability to choose who gets which kinds of messages. The reason this is important for us is that now your domains have been designed to announce business events that the inventory was low. Your domain does not care where the inventory actually comes from. The gateway and the configuration that you have in there decides where you send the messages. So this means that your domain code can be truly abstracted. It can be an actual business domain now, and there is no leakage of non-domain specific logic in there. The second interesting thing is that you now enabled your business to abstract out, allow them to easily replace vendors. So you're not vendor locked in as much anymore, because if during contract negotiations you realize that a specific bakery is charging you a higher rate than the other, and the business wants you to move away from it, the only part of your system which has to change is the adapter. And since the adapter is declarative in style and is basically configuration, it means you have a quicker turnaround time to build another one and say, yep, if I want to move to another bakery tomorrow, even though their protocol for communication is different, my turnaround time is now in days and not weeks, months, or even possibly longer than that. So our turnaround, whenever our client is essentially not locked in, because we can change vendors at a very, very quick pace, which allows our business to make to go into contract negotiations and be a lot more comfortable with with potentially changing vendors. So far, we've been looking at one-way communication. Like we've just focused on requests going out, which is not really a realistic representation of most of your systems, right? Because you usually want to also work with responses. So let's look at what synchronous as well as asynchronous communication here would look like. So the simple stack that we had so far, the reader, transformer, and writer, together make up the request path. And if it's synchronous communication, kind of like HTTP, what you would do is send the message out over HTTP, and you'd get an immediate response. When you get a response, what you do is that you have another reader, transformer, and writer to sort of take the message, immediately process the entire thing, and this together we call as the response path. If you notice something, we have the same stack mirrored in a certain sense. So the concept of a request and a response don't really mean anything for us anymore. It's essentially a pipe of the way you process things. And this conceptually remains true, but there's a few things you'll notice later in the architecture where we had to evolve, where the request and response start diverging. But conceptually, you're doing the same things irrespective of whether it's a request or response, especially when it's a synchronous system. So now if you move to an asynchronous system, the main difference is that you will send a request and your thread is essentially done. We don't want a blocking system. So what we do is we send a message out, and at some point the system responds. Let's take JMS as an example, a classical example of what you do when you have an asynchronous communication. So when the request goes out, you have, we added a component called the correlation ID generator, which basically generates a random ID. In our case, we use a GUID. Doesn't matter if it's a number. The vendor's being told that as part of the message at a very specific place, there will be a random number. There will be a specific number. They're responsible to take that message, and when they send us the response, build a packet which has the exact same number. And that's how we notice. That's how we can correlate the request with the responses. The correlation ID generator not only generates this random number, this correlation ID, but also associates the kind of message we were sending out. As a result, when we get the response and we look up that table for that ID, we know what the request was, and therefore we know how to process the response. Okay, so whenever you start off a new project, you define what the success criteria for a project is. Usually this means a bunch of functional as well as non-functional requirements, functional as well as cross-functional requirements. You go through the inception, you define the scope, everything looks great, you're really happy. As with most projects, as with a lot of projects you would deal with, at some point something would go wrong. Either it is the fact that you're behind schedule, or the release date has to be moved up, or you're running short of budget, so you have to speed things up. A tough decision has to be made as to how you can deliver functional value, or like as much value as you can in the new timelines that you have. A lot of times when reprioritizations to be done, the cross-functional requirements are the first ones that go out of the window, because as a technologist you're not completely happy with this decision, but you understand. You understand until you actually go to production and everything's working fine for a couple of months. It's holiday weekend and you're the one who has to pick up that pager. I think you know where the story is going to go soon, right? You're sitting at the dinner table with your family and the pager goes and your phone rings. You barely have to look at your phone. You know exactly what's about to happen, right? That vendor that you integrated with 6 months ago just went down. Holiday weekend, high loads, it just crashed. And you're the guy who's spending the remainder of your holiday weekend on call. This is not a situation I wanted to be in, and no one else on my team wanted to do this as well. So, because as Murphy's Law states, anything that can go wrong will probably go wrong. So why not prepare for it? So here's a few cross-functional requirements that we planned for, things that we tried our best to make sure that the system has so that it's resilient. The first one's kind of obvious. What happens when you just can't speak with this critical vendor, which is very, very important to run your business? right? So let's look at an example. This is the stack that we've been looking at. Let's look at what happens when the vendor is not available, right? Now, if you're doing HTTP-based communication and the vendor is unavailable, you get an immediate response. The writer will try to send the message, and the HTTP call fails, right? So it's pretty obvious. It's instant feedback. If it's say JMS and the JMS channel itself is down, as soon as you try to send the message, the queue is not available, so it fails, and you get immediate feedback. If the vendor itself is unavailable but the queue is available, what ends up happening is the queue will start filling up. You can put monitoring on top of it and alert on the fact that your queue size is going up. If it goes over a certain range which you deem as being outside operational parameters, you'll probably get a page. You can call up the vendor and check with them what happened. But let's focus on the first two types where you get immediate feedback and errors are just being thrown at an extremely rapid pace. Right? So if you're doing a couple of thousand messages a second, you're looking at that many errors a second. So when the vendor is down, the message goes all the way to the writer, there's an error and an exception is thrown. Since everything is on the same thread pool, exception goes all the way back to the event bus, and since the bus is a queue, it'll just keep retrying. All you have to do is set up a retry policy on the queue so that the message keeps being sent. So, congratulations, you fixed the problem. If you have an outage on the vendor side, or at least on the communication medium, your system just keeps retrying and everything works. So let's actually try to visualize what this looks like. Let's do that with an example. You have 6 messages marked A to F being sent to 3 different systems, 1, 2, or 3. Just for laughs, let's make sure that the first vendor is unavailable. I marked all those messages as red. Vendors 2 and 3 are available, so they will be marked as blue. The expectation is anything which is any message going to vendor 1 will keep retrying. Anything which goes to 2 or 3 should go through. Let's say we have 2 threads to read the message off the queue and process everything, right? So that we'll pick up the first 2 messages, try to process them. Since the first one's not available, it'll throw an error, keep retrying, just like we talked about. Since the second one's available, that message will go through. Everything looks great. Since the second message went through, we'll remove it from the queue. Let's move everything up 1 level. Both messages are unavailable at this point. So what we'll do is we'll throw an error on both of them and keep retrying until the vendor comes up. Now, while this looks like the state that you want to be in, if you look carefully, there is one problem with the system. Messages 3 and 4 are marked in blue. Those messages should have been delivered. There is nothing wrong with that. That communication channel is completely open. However, since there's 2 messages above that and you have only 2 readers, you block your entire system. Congratulations, you have cascading failure. Drucker's law, which is interestingly a corollary of Murphy's law that I didn't know about, states if one thing goes wrong, usually everything else will, and at the same time. So just by trying to fix one problem, we've actually caused a worse problem, which is not only have we blocked the first vendor, we've actually stopped sending messages to everything else, and your system's backing up like crazy now. By the way, you could have replayed that problem with any number of threads and any number of messages. The system will eventually always come to that state. So it's mathematically always going to drop. The way we fix this is by adding, splitting the root into smaller sections. What we've done is that when you're trying to send a message to vendor 1, there's a sub queue 1 up top, and there is a sub queue 2 in the bottom, which is just sending message to vendor 2. The reading and the processing of messages is common. When you process the message, you realize where it's supposed to go, and that's why there is a fork. The buffers that you see at the front of the sub queues are essentially, any queue-based technology. You can use ActiveMQ or whatever else. And what you'd use it for is buffering. So let's look at an example of what happens when you have a message trying to go to an unavailable vendor. Comes to the transform mail, you realize that something's wrong, it needs to go to vendor 1, gets put onto the buffer queue. You then go ahead and process the message all the way to the writer. Since the vendor is unavailable, it throws an exception, but this time it will go back to the buffer because that's the last queue you worked on. You have a thread pool for the section up top. There's a thread pool for this section in the bottom, and there's a thread pool for just the reader writer. So what you've done is whenever there's an exception here on the top, it'll just retry in that smaller loop. Now, if you're trying to send a message to an available vendor, you will see that it just goes through the system, goes to buffer 2, no problems, it will be delivered. Now, when you have extended downtime, the first message is already being retried, but as more messages keep coming in, they will keep getting queued behind the first message. The first message continues to be retried, but the second, third, fourth, the nth message all stay there. If there's a message to an available vendor, you notice that it's going through now. There's nothing blocking it. And this is how you actually alleviated the problem that you accidentally caused earlier, which was the cascading failure we talked about. Now, when the vendor becomes available again, all the messages flow through without any system performance degradation. Let's look at the next challenge, rate limiting of outbound messages. Now, rate limiting seems like a pretty standard problem. You need to do this mainly for two reasons. One, you build this shiny new architecture where everything is cloud-based. You probably, if you're on AWS or something, you probably have dynamic scaling. So every time your traffic load goes up, you could probably just keep scaling and you could take that traffic. Just because you're scalable does not mean that your partners are, right? So if you scale up, you will handle the traffic fine. But when you start sending those increased messages to your partners, if they can't scale at the same rate you can, you will essentially have a denial of service attack on them. This is probably not the best thing for your relationship. You probably piss them off. So the nice thing to do really is to put a small component in there which makes sure that you don't send them more than a certain number of requests. This is something that you'd usually want to talk about during contract negotiations. You want to make sure that either they agree that yep, we can scale up, we don't have a problem, in which case you don't put this in. But if you're talking to a system where they don't have scalability, dynamic scalability, put one of these in. Usually, if you have a denial of service, you end up bringing their systems down, you're actually losing more time. You're better off sending lesser number of messages per second over a longer period than having a spike of large messages and an outage for multiple hours after that. Also, in some vendors, we've actually seen if you send them more than a certain number of messages a second, they will end up blocking your account. And good luck trying to be on call during a holiday weekend and explain to them the fact that you want your account unblocked and it's affecting your business. Because they're probably not barely available and it's going to take forever. So make sure you put this throttler in place. By the way, that story about account blocking, it's real. It does happen. Thankfully, we never had to face that, but it is definitely part of the contract. Okay, moving on to the next problem. What happens when a vendor asks you to retry? In HTTP sense, it kind of looks like a 503 HTTP 503 with a retry after header which specifies a time. So it could say, I'm doing a deployment right now. Why don't you come back after 10 minutes? So this is something we've seen as a pattern. Sometimes you have a custom message type that a vendor returns, which says, whenever you see this header, know that we are unavailable. Please just come back after a certain amount of time. Or sometimes there's no time, in which case you just keep retrying. Just keep doing it. And in the system that we built, the way we do that is that when you get a response and you identify that it is one of those retry kind of messages, you send the message from the response side back to the buffer. The advantage of doing this is that you don't have to process the message from the beginning. If you transformed it the first time, it will look the same way as you doing it the second time, the third time, or the nth time. The data doesn't really change, right? So if you convert an apple into a half-eaten apple, it will always look the same. I guess that's a bad example, but you know what I mean. So the transformation always looks the same. So what we're doing is that when we transform the message, in the correlation ID generator phase, we actually put a copy of the original message as well as the transform message in that database. What we're also doing is that on the response side, when we when we get the response, if the response is is a successful one, we kind of save it in the database as well. If it is one of the retry type of messages, we will kind of maintain a count just mainly for debugging to just statistics to know how many times we had this problem. So if you had to retry a message 8 times, that message will have a count there and we'd know. If it's a non-zero message, we had a problem in terms of delivery, and even though the message came in at say 11 a.m., it actually got delivered say at 11:30 a.m. We had a 30-minute delay. So we can calculate statistics like that, which are important, especially if the customer calls up and says, I clicked the button 30 minutes ago, why don't I see, why didn't anything happen? So those kind of queries, it's easier for us to find out what happened. There's 2 more things which, as a result of this small change to handle retries, we've received. One is that we have a record of every message which has come into our system, the way we transformed it, the way we sent it out, and the response we got from them. So in case you ever have to be audited to make sure that you did the right thing, you have a full log of everything that's happened. I don't know if you worked at an financial institution, you probably know how important the ability to audit your messages are. And as Vinny probably mentioned in his talk, having an event source system is a huge asset. Like auditability is pretty easy on an event source system. On a gateway, this is kind of the equivalent of that, because we have every message that came through, we have a record, and we can prove why we sent a specific message, and nothing was tampered with. Also, as a result of this, we kind of got the ability to do something on real environments that we normally wouldn't have. In case we made a mistake on processing the response, like let's say there's a defect on the response side transformer, right? And while processing the message, you just blew up. You threw an exception. Well, since you have the response that the vendor sent to you, all you have to do is fix the defect, push it to production, and take the same message and put it back into the queue and sort of just push it through the system again. Your system will think that it's a new message and just process it all the way, and the system will correct for itself. You don't have to build in something elaborate. This is like the bare framework that we require is already there. So that kind of system actually helps you recover in case you had errors as well. Okay, let's look at the next challenge, which is what happens when vendors throw an error that you don't know of. For this, we'll take a quick example. So let's say you're running out of cheesecakes. One can't really have enough cheesecakes in their life. So what you'll do is, I basically visited the office. Let's say I ate all of them. So your system then has to go out and order new cheesecake. So when the system announced the fact that you didn't have enough cheesecakes, the gateway notices that and places an order. Your vendor normally should respond with the success message, but instead just gives you a message that absolutely does not make sense for the request you sent. So you're confused, especially because the joke that the vendor just made is at least 4 months behind schedule. HTTP 418. Look it up. So what you end up doing is you're confused about what actually happened, and the only thing you can do at this time when you don't know how to process the message is to find a human being to deal with this message. So this is where we introduce one of the last systems into our ecosystem, a BPM. Steve Carell from The Office. The reason why we have a BPM here is that there's inherent strength in some things that computers do. Computers are great at processing large volumes of data and doing them really, really quickly. But when you have an actual decision to be made, when you don't know what's going on, that's something which is best left to a human being to do. So a business process manager is a system that we use to allow us to sort of manage cases. So what we do in such at such a point when you have this kind of an error is you create a case in this case management group. Now there's multiple systems out there. that you can deal with. Our client actually had one of the systems available, so we just used those. If you've not used a case management system, you can try envisioning maybe a ticket management system, which is kind of similar. You send a request in, it creates a case, and it notes that something had happened. Now, you're expecting that an agent looks at that case, tries to understand what happened, and figure out what needs to be done to fix the problem. Like, the problem might not always be technical. One of the cases we had was that a vendor deleted their zip file, like their standard table where they have all US zip codes. As a result, whenever we sent them an order, they didn't recognize any of the addresses because they'd go to do a check and just say, this is not a valid US address, when it clearly was. When these kind of errors just start flooding your system, a human being can look at it and be like, well, the address looks fine, I verified it. So what this means is that the vendor's at fault. So somebody picks up the phone and actually calls them up and gets them to fix it. Now, if you have the same problem and you have, say, a couple of thousand requests per second coming through your system, by the time the agent logs in, they might see 500,000 different cases. Now, I don't know about you, but I don't want to be the guy who logs in first thing in the morning and sees 500,000 new cases that I have to solve by the end of the day. Right? It does not make me happy. I'd probably end up quitting or something. I don't know. So not wanting to have our people in that position, we had to figure out a more intelligent way to handle these cases. So what we did was we tried to group cases together based on their similarity. Usually, even though the errors are unknown, you can look at a few key characteristics and know how to group them together. You know where the error occurred. You know what kind of error it was. You can use that and along with the system that you got the message from, take all of that and hash it together, and most of the time you would get the same hash. So when the zip code example that I mentioned happened, even though there were 500,000 cases, the number of hashes generated was 1. What we did was, you can tell the BPM to look for this specific code, and every time it sees a code, if the code is the same, do not make a new case, just append it to the same one. So instead of the agent looking at 500,000 cases first thing in the morning, what they actually saw was one case with 500,000 data points. Since this case management tool also allowed automated fixes to be applied, so when we built a script to actually fix this problem, all they have to do is select all 500,000 cases and apply it. Probably go grab a coffee or something and just watch the system fix itself, right? So that's kind of the power of this system. The last challenge we're going to be looking at today is what happens when you have a blue-green deployment being done on a system when you're speaking to a third-party system over JMS. Now, you build this brand new architecture which is really resilient, which always is available, takes messages, processes them, sends them through, is almost, it never loses anything. It's perfect, it's beautiful, it's always available, except when you're about to deploy something. Because the moment you're about to deploy something, you probably will bring it down. Right? There's a brief moment when that your system will be unavailable. There are multiple ways to tackle this in terms of deployments. One of them is blue-green deployments, and which is kind of the strategy that we as a whole selected for our platform. So we'll go through a quick crash course, I guess, of what blue-green deployments look like. So now if you have your user kind of trying to use your website and make calls, what you do is you send the request that comes in from the user's browser into a system like HA proxy or something else which balances the load. Now when you deploy that stack, that standard stack that you see on your left, which is basically a group of domains with the event bus and your gateway. Let's call the stack as the blue stack. The load balancer that you have actually sends every request which comes in from the user to the domain. And the gateway has also been configured to talk to the vendor at the bottom. So far this kind of looks similar to what we've been talking about, right? When you want to do a new deployment, what you do is you take the entire stack that you see on the left and basically deploy a newer version of every one of those services. So let's call this stack the green stack. So now you have the same set of services, and this side is inactive. It's called inactive because it's not actually taking live traffic. It's just there. You want to make sure that it started up correctly. Everything looks great. You've done your automated system checks, and you're like, yep, this is ready to go prime time. This is the newest and the latest and the greatest version of our code, and you want to make sure it goes live. So in blue-green deployments, there's this step called as the swap, where as soon as you hit that button, the inactive side will start taking traffic. So if you just noticed, the green side, which was recently deployed, is now the active side, and the blue side is inactive. Once you notice that all the traffic has drained from the inactive side, everything's great, you will kill that entire section, and you have just one side of production. So this is blue-green deployments done correctly. But this is not what actually happens when you deploy a code, when you do a blue-green deployment. What actually happens is that when you have the active side fully connected, everything's working, as soon as you deploy your newer version of code, since the gateway knows the address of the vendor, the vendor queues, and it's been configured to always be connected. So guess what's the first thing it does when it starts up? It goes out and connects to the vendor. Now it has no messages to send to the vendor, so that's fine. However, the active side is sending messages. Now you have two different versions of the software who are both trying to read the responses, which means there's a 50% chance that your inactive side that you not confirmed that it's correctly working yet is actually taking traffic. This is an anti-pattern. Unless you're ready, you don't want it to take traffic. So the side that you want it to be inactive is actually active. This is blue-green swaps done incorrectly. Well, actually, you've not even done a swap yet. So this is just blue-green done incorrectly at this point. So the way you fix this problem is the same way you fix a lot of problems in software development. We fixed this problem by adding another layer of abstraction. So what we did was we added this layer called as the messaging proxy. Now this is kind of similar to the thing that you see on the top. We used HA proxy, which is the same component we used here as a load balancer. Except this time when we configured it here, we configured it in TCP mode. So as soon as you try to connect to a queue, the gateway is being given the address of the message proxy and not that of the third-party system. The message proxy essentially, well, as the name suggests, proxy is the connection to the vendor. So in this diagram, the gateway on the blue side thinks that it is talking to the third-party system, but it's actually talking to the proxy, which is just relaying messages through. Right? It's really quick. It's a transparent proxy. It's not a performance hit, but there is an advantage. The advantage is that when the green side comes up, it tries to connect both both to read messages and to write messages. What we did was that the message proxy, the blue and the green side have been given different port numbers. Let's say this is on port 1, 2, and this one's on 3 and 4. So what we've done on the inactive side is the port which is actually used to read the messages has been disabled. So when the inactive side tries to connect to it to read messages, it just can't. As a result, what you'll see is that it can't pick up messages. So that's why the inactive side stays inactive. The moment you actually do a swap, what you do is not only do you tell the HA proxy on top taking the HTTP traffic to switch over, you also tell the message proxy at the bottom to switch over. So it will now make both the ports which have been configured for the green side to talk to go live, and the other side it can just have one connection. The reason why we still have the outgoing connection on the new inactive side is just prior to swap, if there's a message which came in and you're still processing it, you don't want to lose this message. You want to make sure that it goes through, right? So let's say half a second or whatever is the standard processing time. A couple of 100 milliseconds later, when you're done processing the message, it will actually write it out. If the vendor responds to that message, it will never go to the inactive side, it will go to the active side. And all the traffic now starts flowing over to the new active side, and within a few seconds or minutes, you'll notice that the inactive side there's no activity there at all. You have monitoring on each of the services and queues. and that's when you can switch it off. Congratulations, you made it through the entire thing. Time for the summary. So, scale your integrations. Use declarative integration definitions wherever possible. They're quicker to do and easier to manage, and they also act as documentation in themselves on how what's the communication protocol between your systems. Try to be vendor agnostic and have vendor replaceability on your system. Right? Agnostification allows you to build better domains, well abstracted domains, which focus purely on business concepts and not on system specific concepts. And if you do this correctly, you have the ability to replace vendors with a lot more ease. This is great because your business will appreciate this fact a lot. Making your business happy is probably the best thing a dev can ever do, apart from delivering projects on time. Next thing is plan for failure from day one. Always, build resilience from day one. Always plan that something or the other will go wrong. Just because you're scaling your system dynamically does not mean that your vendors will scale them dynamically. Be nice to them. Have the conversation up front. Make sure they can either scale as quickly as you, or that you put in safeguards that you don't cause them problems. You don't want them to be angry at you. Have recovery plans in case of failures, and always assume that every single component in your system can fail. Always have a backup. Automate error handling wherever possible. When error handling is not possible, use a BPM. When building a resilient platform, it is important to build a system which is not severely affected by issues outside your system. Building resilient systems definitely makes Spock happy. Sorry, I could just leave that out there if you just want to enjoy and dance. I love that kid. I said thank you once again. My name is Karan Jaffer. My contact details are up on screen. In case, I'd love to hear your feedback on the talk. So if you're tweeting, please, feel free to tweet at my handle or send me direct messages. Slides are up there as well in case you want to see it and know certain people in the crowd have already done that. And I'm available for questions now. Thank you.
Can you just maybe give us a hint regarding the technology stack you guys use? Of course, I understand there can be several platforms to use, but which is the one that you guys tried for the bus and for the adapters and gateway?
Okay, so I'll repeat the question. The question is, what kind of technology stack did we use for the event bus, mainly around the event bus and the adapters and the other stuff that I talked about. For the event bus, we ended up choosing ActiveMQ. For the adapters, we built something custom made. The reason is that we wanted a declarative style to do transformations. Generally, most people have pure code just written custom one time to be able to transform stuff. But what we wanted was, a lot of our semi-business-ish users wanted the ability to do transformations themselves. So they're like, we want to write something which is very, very easy to configure. It should essentially be configuration that is easy to understand and make sure that it's right. So, so we built a framework which helps them do that. And if you want, offline I can show you what some of that looks like. I have a couple of hidden slides I skipped over. So yeah, custom framework for the transformation bit. Just so we could do it across runtimes as well. So in case you want to, this is a real-time environment, if you want to do data porting over Hadoop or something like that, we had requirements that we wanted to use the same set of transformations because transformations in themselves are treated as assets in the organization. So when you're talking to a specific vendor, the language is kind of defined, right? So if you have the language defined, you want to reuse that same language across multiple systems to make sure you don't rewrite the same code. So we had to roll out something custom to make sure that all the runtimes the business work, that the organization works, and we could apply the same thing. So we had to roll something out custom. So I think you are next, and then.
Did you have any cases where your transforms weren't purely functional, so either they depended on states or they didn't map one from your data to any?
Oh yes, the function. You're right. So sorry, I'll repeat the question. Did you ever have a case where your transformations were not purely functional that required state to be maintained? We actually grappled with that question quite a bit, right? So the idealistic view that we built in our heads when we started the project was, hey, everything should be purely functional, purely stateless. If, having states or having mutations is not great. Let's build this idealistic garden where everything looks amazing. And that works very well, and it does most of the job that we want it to. Every once in a while, it does not. So we had the question, I think, is that yes, we had that, we had to handle it. The way we ended up handling it was the question we had to answer is whether we wanted the framework that we were rolling out for transformations to support mutation out of the box, or did we want to build a more generic framework where we allowed the user or the end developer to actually do that. So what we did was we built transformation functions where you could have hooks to say, there's a data provider here. So when you did map field A to B using function X, you would say in X I have to take A is given to you, so you just do a query or whatever else, and that could maintain your state. So we allowed users to do that from inside that sort of sandbox that we have. So that's how we solve the problem. It's not, it kind of is tricky because every once in a while, if you have an external integration, that could fail, and that means that your transformation overall could fail. So you had to handle more and more error cases. But yeah, I mean, we ended up doing that and making sure that the sandbox we built for them is safe, is resilient in itself, and put retry policies in there to say if a database is unavailable, we can't transfer your message. So we'll throw an exception, we will handle that in a separate way. That's probably a topic in itself for discussion.
Give an example of a declarative integration configuration as opposed to something imperative.
Guess I'm pulling the slide up. Okay, give me a sec. So I'll try going full screen. I don't know if Keynote will let me do this. Oh, sorry, you guys just see my desktop. It's a random wallpaper. Oops, no, I have to unhide those slides. Let's try this again. Okay, cool. That's what, I mean, to your question earlier, what does the transformation kind of look like? I mean, our declarative transforms kind of look like that. It's essentially saying I need to transform, I'm going to skip the concept of a selector and target just for now, but the map bit is the actual transformation. You're saying that map an item ID to something which is an item ID in uppercase. So your source is on the left and your target's on the right. And you can also pass in a transformation function inside the two right after the target. So that's what that looks like. That's the transformation rule overall. Like I don't have full examples to say. A non-declarative one would be, you can imagine as just a Java function where people are taking an object of type X and converting it into an object of type Y. Like we didn't want to build object-to-object physical mapping where you're doing object.get and set it to other object.set or constructor or whatever else. Like that's kind of code we didn't want to sit and write because it's hard to test and maintain as well.
You couldn't use Spring Beans?
We could do that as well. We actually couldn't use Spring in this particular project. One of the requirements I mentioned was the fact that we had to have the ability to run this over multiple runtime environments. One of the environments that they wanted us to run in, they couldn't have Spring, the entire Spring container there. The initializing container would not let you start out with Spring. So we had to go no Spring on all of the project, like at least the adapter bit. The other stuff you can have, like the gateway has Spring on it because it's the container which runs the code.
Okay, let's take one more question and then you can take it offline.
I think there was someone here who raised their hand first. Or
Yeah.
sorry, I'll be right back.
I was just wondering if the diagram was simplified, but like the calls between reader, transformer, and writer, like what protocols were that, or was there queue in between, or so just like call to call?
It was just call to call at the time, which is why I said like one of the things I mentioned was when you have an error, it just the stack just goes back all the way.
Okay.
So we just use the same thread across. I guess in a more SCDF or Spring Cloud Data Flow manner, if you've seen the framework, each of those steps would be a processor in itself and could be separated by a queue, is separated by a queue, right? So and that's a similar sort of concept, but slightly different implementation. One of our key requirements was, since transformation and message sending is an overhead, and traditionally the organization had direct calls, they didn't want this framework to take up too much overhead. So the requirement we were given was you can take no more than 10% of the time that the pure call takes. So if the call is 100 ms, like all the persistence, everything else can take no more than 10 ms, right? And as much as we tune our databases, like the database calls we made, each of them is 5 milliseconds for us. So which means you don't have much room to actually do the transformations. So if we did one of the queues would have to be backed up, and one of the requirements is that each of them have to be persisted in case of failure to make sure that nothing happens. That adds disk IO time, which makes everything longer. So putting queues would have just blown our budget. So, pros and cons.
Yeah, so you're already running, right? So sorry. So you can take it. Karun will still be here, so you guys can ask questions.
I'm still
offline.
around.
Yeah, I just have a couple of points, right? So one, thanks everyone for coming. I hope you guys enjoyed it. There is a feedback board outside, right near the entrance. There are stickies, and you can leave feedback about the talk, about the meetup. What do you want to hear about? Like any other topics that you want to hear about. We take that feedback seriously and kind of work on it and kind of improve as we go. Another thing is, there's still some beer left, so help yourself. Mingle, network, and another thing, if you have any questions after today, you can either tweet or email Karun. I guess you should go back to that slide so people can note down that. Or you can also go to the discussions tab on Meetup and actually post questions there, because we will be monitoring that and kind of answering questions. Okay, thank you everyone.
Thanks everyone.